Ladies and gentlemen, this is the fourth lecture in the module of Lean Six Sigma, Measure Phase. During the lecture, Part 1 of the Measurement Systems Analysis will be covered. During the two lectures, we will perform the analysis manually, by hand, and using Sigma XL, and also using Minitab. The measurement systems is divided in two sectors: measuring system analysis for continuous data, MSA, measuring system for attribute data, kappa. We will perform the measurement system analysis to determine if a measurement system can generate accurate data. It checks the quality of the measuring system, not the quality of the product. Types of MSA are gauge R&R, bias analysis, stability analysis, discrimination analysis, kappa analysis. There are different types of measuring instruments, like avometer, thermocouple, vernier caliper, micrometer, stop switch, and sound level meter. All these instruments measure a physical quantity in the quality assurance and engineering. Measurement is the activity of obtaining and comparing physical quantities of the real-world objects and events. The output data from these instruments are used in the quality assurance and quality management. Every gauge has its own specifications. However, the most important parts in the gauge specifications are the range and the resolution. The range is minimum and maximum physical quantity that can be measured by the gauge. And resolution is the smallest change that can be measured. Finer resolution reduces rounding errors, but doesn't change a device's accuracy. However, resolution that is too coarse may add rounding errors. Measurement error is equal to the measured value minus the true value. There are two types of measurement errors: the systematic errors, offsets or biases, and random errors, characterized by the variation. The systematic error is the value by which an instrument's reading are off from the true or master value. Systematic errors are estimated and corrected during equipment calibration. Random error can happen due to operator variation or instrument variation, and it is corrected by gauge R&R study. Measurement errors are estimated using accuracy and precision. Measurements need to be precise and accurate. Accuracy and precision are different, independent properties. Accuracy is how close a measured value is to the actual, true, value. Precision is how close the measured values are to each other. Data may be accurate, reflect the true values of the property, but not precise. Measurement units do not have enough discriminatory power. Vice versa, data can be precise yet inaccurate. They are precisely measuring something that does not reflect the true values. Sometimes data can be neither accurate nor precise. Obviously, the goal is to have data that are both precise and accurate. The accuracy and precision of a measuring instrument are to be determined. An operator measured the length of a standard gauge block of 50 millimeters for 10 times. The measured values, length in millimeter, are shown below. The mean value is 50.2, and the standard deviation for measurements is 0.123. The true length of the gauge block is x, which is equal to 50 meters. The accuracy is equal to x bar minus x, which is equal to 0.2. The precision is equal to 6 multiplied by s, which is equal to 0.737. The precision is calculated according to the Six Sigma precision, based on the normal distribution. Measurement errors are estimated using accuracy and precision. Accuracy and precision are broken down into components shown below. Accuracy is how close a measured value is to the actual, or true, value. Systematic errors are measured by linearity, bias, and stability. Precision is how close the measured values are to each other. Random errors are measured by repeatability and reproducibility. Bias, referred to as accuracy, is a measure of the distance between the average value of the measurements. Linearity, a measure of the consistency of bias over the range of the device. For example, if a bathroom scale is under by 1 kilogram when measuring a 75 kilogram person, but is off by 5 kilogram when measuring a 100 kilogram person, the scale bias is nonlinear in the sense that the degree of bias changes over the range of use. Stability refers to the capacity of a measurement system to produce the same values over time when measuring the same sample. As with statistical process control charts, stability means the absence of special cause variation, leaving only common cause variation, random variation. Bias is a systematic error for the gauge. Bias is equal to observed average minus the true value. It is the difference between the observed average value of several measurements of a sample and the true value of that sample. True value is equal to theoretic correct value. For example, measuring same object with same gauge with same operator n number of times. Consider the following 10 measurements by an appraiser. The true value determined by layout inspection equipment is 0.80 millimeters. The observed average is the sum of the measurements divided by 10, which is equal to 0.75. Bias is equal to observed average minus true value. Bias is equal to 0.75 minus 0.80, which is equal to minus 0.05. Linearity is the difference in the bias values through the expected operating range of the gauge. For each measurement instrument, there is a low end of the range, and it is the minimum physical quantity to be measured, and high end of the range, which is the maximum physical quantity to be measured. The linearity is the difference in the bias when measuring the low and high end of the range. Diameters of two products representing the range were measured using a micrometer. 10 readings were used for each product. Master is equal to 2.5 millimeters and 5.5 millimeters respectively. To assess the linearity of the gauge, as follows. Bias for part 1 is equal to minus 0.01 millimeters. Bias for part 2 is equal to plus 0.01 millimeters. Then, linearity is equal to plus 0.01 minus 0.01, which is equal to plus 0.02. Stability is the difference in the average of at least two sets of measurements obtained with a gauge over time. Let x1 bar is the average observed measurements at time t1, for example week 1. Let x2 bar is the average observed measurements at time t2, for example week 2. Stability is equal to x1 bar minus x2 bar. Instability occurs due to wear and deterioration and environment. Length of a batch of 10 parts was measured using a gauge at 8 a.m., and the same batch was measured again at 2 p.m. using the same gauge. Results of the two set of readings were as follows. Stability is equal to x1 bar minus x2 bar, which is equal to minus 0.05. Calibration is used to correct instrument inaccuracy by comparing readings of the master gauge to the instrument we need to calibrate. The line represents a perfect gauge. Deviation from the line is equal to error of the gauge at that true value. Using the true value readings and the instrument readings, we draw the calibration curve and determine the calibration equation. Then using the calibration outputs, we can correct the instrument readings. If an instrument or gauge is used to measure several parts from a process, and the results are recorded, then the resulted data represents the variation in the parts, as well as the variation in the measurement process. Data variation is equal to parts variation plus measurement variation, which is equal to both gauge and operator variations. Random errors are caused by variability or random variation due to differences in the gauge and/or differences among operators. Actual process variation with no measurement error, and this is the true value. Observed process variation with error in measurement. Readings tend to be wider, inflated due to error in measurement. A good measuring system is that, with total variation is coming from the variation of part to part, with no gauge or variation of the operator. As we learned before, the total variation in observed data is equal to the variation of parts plus the variation of the measurements, which is equal to the variations from both gauge and operator. Repeatability, the variation that occurs when successive measurements are made by the same person over and over with same part, same gauge, same setup, and same conditions. It measures the variation by gauge. Repeatability is precision under repeatable conditions. In the case shown by the figure, the repeatability, the variation by the gauge, of gauge A, is better than that of gauge B, as shown by their probability density functions. Reproducibility, the variation in the average of the measurements made by different operators using same equipment, same parts, and same other factors. It measures the variation that occurred when different people measured the same item or same gauge. The variation in operators. Reproducibility is the precision under reproducible conditions. Part variation. The part variation is essentially a measure of the variation of the process. If a large number of parts made by a process are measured, 99%, 5.15s, of the parts would be within the variation limits. The part variation is always less than or equal to the total variation. In most industrial processes, the part variation is large compared to the variation of the gauge. Again, the variation of the part is less than or equal to the total variation. Meanwhile, it is greater than the variation of the gauge. Measurement system error is a primary cause of possible sources of process variation. Variance of the observed process is equal to the variance of the actual process plus the variance of the error of the measurement system. Variance of error of the measurement system is equal to the variance of the repeatability plus variance of the reproducibility. Variance of the repeatability is equal to variation due to gauge. Variance of the reproducibility is equal to variation due to operator. Measurement system analysis will be done in 4 steps. First, measuring system accuracy, which is expressed in 3 values. Bias. linearity. Stability. Second, measuring system precision, error due to variation, sigma of measuring system, is calculated from variance of the measurement system is equal to variance of repeatability plus variance of reproducibility. Use sigma of the measuring system to calculate gauge R&R ratio. This ratio should be between 10% and 30%. Use sigma of the measuring system to calculate precision to tolerance ratio. This ratio should be between 10% and 30%. Addresses what percent of the observed process variation is taken up by the measurement error. It includes both repeatability and reproducibility. As a target, some industries look for percent R&R, which is less than 30%. QS 9000, Ford, requires percent R&R, which is less than 6%. Gauge R&R percentage is equal to sigma of the measuring system over sigma of the observed of process variation multiplied by 100. Precision to tolerance ratio is a measurement system capability index. It addresses what percent of the part tolerance taken by the error of total measurement, or sigma of the measuring system. Sigma of the measuring system include repeatability and reproducibility. For best case, precision to tolerance ratio should be equal to 10%, and, for acceptable cases, precision to tolerance ratio should be equal to 30%. Using 5.15 as an industry standard, where 5.15 standard deviations accounts for 99% of measurement system variations. Precision to tolerance ratio is equal to 5.15 times sigma of the measuring system over USL minus LSL. Thank you, and see you in the next lecture of the measure phase, the second part of the measurement systems analysis.